All right, 7th grade students, let's go ahead and do a quick recap here. Today's notes are going to be quick, simple, but there's a lot to cover here. And so one of the things that I've done is I've kind of rearranged and cleaned up some of my notes. So a little bit of this will be writing, and some of this will be just me talking through some of the finer details here. So let's go ahead and take a look here. First, we just want to kind of recall this idea that we're talking about the atom. All right, and the first kind of idea about the atoms come from the ancient Greeks in about 500 BC. And it comes from this guy right here, Democritus. Okay, so we've given that some thought. We talked about Aristotle and his role, and we started this idea of the first version of the atom. Okay, so John Dalton, that guy, in the early 1800s, right around 1803, 1808. 1808 is kind of like the well-established date for this. John Dalton, being in his 30s to 40s at the time, kind of wrote out this first atomic theory. Now, he didn't just do this. He was actually known for quite a few different experiments and things that he studied. He was kind of like the equivalent of a high school or a college professor. And so he came up with this first atomic theory, and so it's all right here. And we also went over this in class. First of all, that these atomos exist, right? And that atoms of a given element all share the same mass and properties. Okay, that we're going to talk about that in just a second. And then there's this idea that you can combine them to form all sorts of neat things. And last but not least, in chemical reactions, they kind of rearrange themselves. So this is the basic atomic theory, and we're going to keep coming back to this and looking at how it changes as new discoveries come into play. All right, so that was kind of version 1.0, and that was basically the equivalent of about 2,300 years from the time of Democritus through John Dalton. Okay, now John Dalton's atomic theory suggested that atoms can vary in size and properties, but they can't be broken into smaller pieces. So this is what they would kind of look like. You'd have a different collection of atoms, and they would have different properties. So I have a green one here, a blue one, a pink one, kind of a red, and a purple atom. And these would be different elements, different sizes, kind of referring to the fact that they would have different masses. And so this is what kind of John Dalton kind of hypothesized through his atomic theory. At this time, we also know that the smallest atom was, and still is to this day, hydrogen. And so this tiny little pink speck right here would be the equivalent of hydrogen. Okay, so we have different atomos, so to speak, for different elements. Now, this is all version 1.0. In 1897, so almost 100 years later, okay, so 1897, we see something really significant happen. We see that this guy right here, okay, JJ, all right, he kind of had a really important moment where he saw the light. And this is not a figure of speech. This is an actual reality. He saw a light, and this event kind of reshaped our understanding, or started the reshaping of our understanding of the atom. So, to kind of break it down, J.J. Thomson was experimenting with these things called cathode ray tubes. Okay, cathode ray tubes, and those look like this. That's a cathode ray tube. All right, so it's actually at this end that you would find the cathode. And there's a bunch of other equipment and things in there, but basically, and down here at this end, you'd have the screen. Okay, and this is a similar type of cathode ray tube where we are shooting a beam through that tube, and notice that that beam is kind of like an eerie green color, like alien green. All right, so yeah, so this is what J.J. Thomson was working with, okay? And so we kind of in class, we drew up this simple little diagram where we have the cathode, and the really remarkable thing about this was this green kind of like laser beam that went up through the tube there. And what was interesting about this was this idea that this beam could be bent. And this was bizarre because there really should have been nothing in this tube, let alone this beam. And when this beam was there, it could be bent, and it was bent by these kind of electromagnets. So these crazy strong, kind of like electromagnets. So these electromagnets could, depending on the way that you turn them on or off, or you could switch, their polarity. So magnets have a north and south pole. If you could switch that, you could actually bend this beam either up, or you could also bend this beam down like that. And so you could actually change where the beam was going. And so here's kind of a drawing, or you can kind of see in this particular drawing, we have the beam, and it is right here. Notice how it's deflected up onto this screen right here, like so. Okay, so here's the big ideas that came out of this. First of all, J.J. Thomson was able to determine that this beam was actually made of tiny little particles. And because of the way that he manipulated the magnets, he was able to determine that these tiny little particles right here, all had negative charges. Sorry about that. So, because they have negative charges, okay, that's what allowed them to be bent or pushed towards or away from the magnets. Okay, magnets can be used to kind of like repel or attract something that is charged. In this case, these tiny little negative particles. So, J.J. Thomson said, well, if there are these negative particles, okay, then they must be atoms. Except that when he weighed them, he had something really strange happen. It was this, so if we think of it kind of like a balance here, okay. All right, in theory, and if I actually redraw this balance, in theory, at the time, there could be nothing smaller than atoms. And so, all right, so what we should have seen was that, hydrogen would be lighter, being the smallest thing in the world, than these negatively charged particles inside this tube. And so we're just going to kind of draw these with a negative charge. And there's that big green negative charge right there. All right. However, that's not what happened, right? So if we back up the boat here for a second, when JJ actually measured these, hydrogen was on this side of the scale. It was heavier. And these particles, these negatively charged particles over here, well, they were lighter. And so this kind of just blew open the water, blew open the mind, the coffers of science, and just like, whoa, what is this? So negative particles smaller than hydrogen. A particle smaller than an atom? This was bizarre. And so this was unheard of. Atoms were supposed to be the smallest, period. And J.J. Thomson's experiment proved otherwise. So J.J. Thomson actually called these particles corpuscles, and that actually means small body. He recognized that these were the smallest known thing now is part of the scientific community. They were smaller than atoms. There was nothing that we knew that was smaller than these mysteriously green glowing particles inside these cathode ray tubes. These particles today are now called electrons. Okay, so to back up the boat, we went from this idea of having atoms, like this atom of hydrogen as being the smallest, and all of a sudden, we now know that there's something that's negatively charged that's smaller, and we're going to call that something an electron. And this opened the door for what we now know as kind of subatomic, sub meaning below, so below an atom or under an atom or part of an atom, this study of subatomic particles. Electron was the first confirmed particle that was smaller than an atom. Now, this also raises lots of questions. Questions like, okay, if there are negative particles in the atom, where are they? How do they fit into this idea of an atom? Because we thought atoms looked like this. They were just kind of like a big sphere, like a marble. But that's not the case. And so we have to kind of come up with a model that would work with this idea. So that leads us kind of to our next page of notes. And that would look something like this. New problem. Where do electrons fit into the mix? Well, this, there were a lot of theories that were floating around. But ultimately, we knew a couple of things. First of all, if we looked at John Dalton's atomic theory, we knew or know that atoms are little round objects. And according to J.J. Thomson's experiment, we know that there must be these tiny particles inside the atom, though we don't know where. We'll just kind of place them in here, like so. And if we left it at that, that wouldn't work, because they knew that in measuring material, that it had a relatively no charge. For instance, if I were to go up to some nitrogen gas or oxygen gas and I were to hold up a magnet, if it was only negative, then every atom would be repelled by a magnet. So that doesn't work, because we know that a magnet can be near wood, a magnet can be near stone, a magnet can be near some other metals, magnets can be near water, and it doesn't repel those materials, which means that atoms themselves cannot be charged. Okay, so if we're looking at this atom here, and it's got all these negative particles inside of it, well, if that's going to make the atom negative, we can't have that. So we need something to balance it out. Just like in mathematics, if you want to do the opposite of addition, okay, you choose subtraction. Same thing's true in magnets. If you have, it's kind of like having two poles, like north and south. Okay, so if you have negative charges, like this little guy right here, then you need something like a positive charge to balance it out. There was a scientist, there were several, but one of them was, his last name was Goldstein, and he said, and he was kind of right around the same time as J.J. Thomson, maybe even a little bit before J.J. Thomson. He had started to guess, and some of his experiments had started to show that these positive / negative properties of atoms existed. So it wasn't necessarily surprising, or it kind of confirmed Goldstein's research that there could be something positive and negative about the atom. And so the question now is, are there positive particles in here, or are there positive something in the atom? We don't know. So this was the conundrum. How do you model the atom? How do you come up with a way of describing this brand new revolutionary idea that there are particles smaller than atoms? They've got to be in there somewhere. Okay, so it'd be like picking up a suitcase that's super heavy. It's not like you just don't assume that the suitcase itself is heavy. You assume that there must be something in there that's making it heavy. Okay, this is like that. We have these particles, they're in there, and we don't know what that looks like because we can't see inside an atom, just like you can't see inside that suitcase. So you have to predict. You have to try to explain the data. So JJ, being the one that kind of discovered these particles, he's like, okay, I'll come up with something. So bam, the plum pudding model. That's right. You heard it here first. The plum pudding model. Absolutely fantastic. You may be wondering, what? Plum pudding? What's plum pudding? How did we go from atoms to food? Now I'm hungry. Need to take a break. Go get a snack. You may be wondering, what's going on here? Pudding? Plum pudding? Don't really like plums. All right? Plums are, you know, they just don't mess, they mess with my digestive system. And you're like, okay. So regardless, in the UK, puddings aren't like the pudding cups that you have with your lunch. Puddings are like tiny little cakes. So this is a plum pudding, and it is yum. It's kind of like a little cake, and it's served as kind of like a dessert. So notice that the pudding is really like a bread. So it's like a bread pudding if you've ever had a bread pudding. So this would be like pudding right here. And in that pudding are plums. Okay, this would be plum pudding. It's kind of like a little fruit cake. Okay, so J.J. Thomson said, what if we thought of the atom as plum pudding, where you have the positive pudding, which is all this entire green area. So all the green in and about here. Okay, so all this space right in here. And then dispersed in that green pudding-like goo would be these negative fruits, which we now know to be called electrons, or as JJ called them, corpuscles. Okay, so this was his idea. Now, if you look closely here, you'll also see that for every negative, there should be a positive. So there's a negative positive pair, negative positive pair, there's a 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 pair, and here's a funky pair right there. Every negative is balanced out with a positive. That means that the positives and negatives cancel each other out, and these particles are happy to kind of exist in this positive-negative pair relationship. So this is officially known as the plum pudding model. That's J.J. Thomson's. Mr. Bornheimer likes to call this the chocolate chip cookie model because we don't really eat plum pudding here in the United States unless it's part of your culture, your heritage, or we kind of call it just fruitcake. So, in my opinion, this looks a lot more like a nice, delicious, delectable green chocolate chip cookie. Again, talking about food. Okay, well, this was a big idea, and J.J. Thomson's model of the atom continues on. Okay, so remember, he kind of came up with this idea in like the late 1800s, and this idea stuck around for a couple decades. There is a scientist, and his name was Ernest Rutherford, and he came up with an experiment to test J.J. Thomson's model, and that test that's going to test that is known as the gold foil experiment, and that's where we will pick up with our notes moving forward when we are back in class, hopefully on Thursday, but if not Thursday, then Friday. All right, these were your notes. Make sure that you write them down. A couple things that I really want you to make sure that you have down. Okay, first of all, make sure that you have down that Democritus kind of introduced this idea of atomos in 500 BC. Make sure you have written down that John Dalton really introduced the first atomic theory, and this was really the first versions of the atom right here in the early 1800s, right around 1808. And it's important to note that the smallest known substance to mankind at the time was the element hydrogen. Because in 1897, important, J.J. Thomson discovers a particle in an eerie green ray that is smaller than hydrogen. Okay, which means that it's smaller than the smallest known atom. Okay, so it's important to note that that atom was hydrogen, and it was smaller than that. And so these small bodies, J.J. called corpuscles, were later named electrons. Last but not least, in order to be able to fit this into a new version of the atom, they had to come up with the plum pudding model. And last but not least, this kind of fulfilled this idea of version 2.0. So the plum pudding model here is version 2.0. So we went from having just a indivisible, uncuttable atomos to having this pudding-like model that had corpuscles or electrons inside of it. And like I said, in order for this to kind of continue to develop, we're going to need to study an experiment that tested this idea, and we will do that in class when we join back together. Thanks for watching. If you have any questions, go ahead and email me. Otherwise, make sure you have these different pieces and drawings and diagrams in your notes. You can go back, pause, rewatch, and make sure you get this down.